So this is the second video related to this worksheet. It's all the way at the back end of this sheet, and it's about a single concept. Well, prior to this video, we talked about what happens when no work is done on or by my system. What happens is that the energy doesn't change. Let me erase what we got here. So when work is done on or by my system, the system's energy changes. How can it change? Well, it could change in kinetic energy. Its potential energy could change, or it could do work against friction. So any one of these changes are possible. All of them are possible, or some of them are possible. My work done on my system could only change the KE or only change the PE, or a combination of all three of these. So let's look at when work is done on or by my system. So neglecting air resistance, so there's no work done on my system by air resistance. How high would a mass, a rock of this mass, go if thrown straight up by someone who does 115 joules of work? So 115 joules work is done on my rock. So when work is done on a system, its energy changes. Well, when you throw a rock, what's the energy change? Changes in kinetic energy. But as the rock goes up, all that kinetic energy turns into PE, where at the peak, which is what we care about. How high will it go? That's the peak height. So there's 115 joules of work done on my rock that goes to KE, and then that KE goes to PE, and it's mg delta H. So you're given the M, 0.325 kilograms. You're given, well, you know the G happened on the Earth, and you don't know the H. And when you work it out, the algebra, it's pretty simple algebra there. So when you work it out, it goes to a height of 35.4 meters. So once again, when you do work on a system, you change its energy. The throw gives the rock kinetic energy. As the rock goes up, at the peak, all that kinetic turns into potential, because now no work is done on my system. The total energy doesn't change. Hammerhead with a mass of this 2 kilograms falls onto a nail from a height. So what kind of energy did it have? That's potential energy. How much work is done on the hammerhead? So you've got this potential energy. Is mgh, and it falls. What does it turn into? It's going to turn into work. It's going to smash the nail and do work. How much work could it do? Well, it can only do this much work, mgh. So m is 2.0 kg. G is 10 meters per second squared. And the height that is given is 0.40 meters. And that's how much work it could do. That turns out to be 8 joules of work. When you do the M, well, maybe it should be 8.0, yep, joules of work, because we've got two significant digits. And there you go. That's number 2. Number 3, we've got a mass, a car, going at 110 kilometers per hour, which fortunately they give us the meters per second, and it comes to a stop. How much work was done? How much negative work is done on my car? It says don't solve it, show the work. Well, the work to stop, work is done on my system in stopping it, and it equals the change in kinetic energy. And that of course is going to be negative. It's 1/2 mvf squared minus vi squared. That it stops, so that's 0. And so we see we're going to get a negative change in kinetic energy. How much? Well, the change in kinetic energy is the work, and you'll get some negative number. It's not important to plug it in. Where did the kinetic energy go in stopping? A lot of it went to what's called internal energy. So the brakes get really hot. And maybe it makes a little bit of sound as it brakes. Probably not that much these days. These brakes don't make that much sound, and but mainly it goes to internal energy or heat. The brakes get hotter. So when work is, what kind of work is it to stop a car? It's negative work. How much work did you do? Well, what was the change in kinetic energy? When you do work on a system, that system changes energy, and there's no mention of potential energy change. Why? Because there's no height change. If they didn't mention any height change, how could you find a change in potential energy? Now, this is what we did already, so we're not going to do a lot of. We actually did this problem. Baseball with this mass traveling at this speed, v, goes backwards in a mitt. The mitt is doing work, it's doing negative work when it's caught. What is the average force? So the mitt did some work, or the glove, and that equals the change in kinetic energy. Like I said, we did this already. So the force of the glove times the distance the glove moved, which is right there, equals 1/2 of m times Vf squared minus Vi squared. And then you plug the numbers in. It's no longer a physics problem, but a math problem. You've got the d, you've got the m, this is 0, and you got the Vi. So like I said, we do that already. This one's a nice, interesting problem. Number 5, it's a multi-step problem. There's a lot of problems associated. In a high jump, the kinetic energy of an athlete. No, wait a second. I'm skipping. I was talking about 6. We got to go over here. Kinetic energy of an athlete is transformed into potential energy, right? She jumps, and at the bottom she has kinetic energy. At the peak she has a potential. What is the minimum speed that must the athlete leave the ground in order to lift her center of mass 2.10 meters across a bar with a speed? Okay, you've got kinetic energy at the bottom. Uh, At the top, it's transformed into potential energy, and she also has some speed already. Also, the kinetic, she's all kinetic on the bottom. When she gets to the peak, she has both potential, we're told, and kinetic. What's the minimum speed that the athlete must leave the ground in order to have a potential energy, a height, and a speed that's given over here? So I don't know if this is so much of a. This is actually not a work energy problem. This is actually just a problem of conservation of energy, that she's all kinetic at the bottom, and at the top she's kinetic and potential. So this is sort of the old stuff. So we go 1/2 mv squared, all kinetic, and then at the top she's mgh plus 1/2 mv squared. And it's interesting to see that all the masses cancel out, so mass doesn't even matter. And so 1/2 the velocity that we do not know equals 10 meters per second squared times the h, which we are given 2.10 meters. No, it's just lift her center. 2.1 meters plus 1/2 of, now she's got a velocity that we do know, 0.70 meters per second, and that is squared. And so I might multiply everything by 2, get rid of the half. This is 20 times 2.10 plus 0.70 squared. Just getting rid of the halves that are here, and now it's just a math problem. Let me give you this. Do I even? Yeah, let me give you the solution. I don't even have the solution. You know what? That's not the important thing. You can do math all day. There's so much more to conquer. So it's this, whatever these turn out to be, add them and take the square root. So I don't have the answer, but that's not the important thing here. Let's clean this up.